in module 2 we have discussed matrices, okay, and in the first lecture we talked about matrices as linear transformations of vectors. Okay. Then in the second lecture we talked about special matrices, we talked about symmetric, orthogonal, Hermitian and unitary matrices. Then in the third lecture we talked about rotational matrices and we talked about eigenvalues and eigenvectors of matrices. And then in the fourth lecture we touched on determinants and we talked about inverse of matrices. Okay. So now this material you can find in Macquarie first edition chapters 9 and 10 or Kreyszig 8th edition chapters 6 and 7. And let me emphasize that in both these books they do many more things with matrices. Okay, many more things with matrices and determinants and vectors, okay, such as change of basis, they look at transformations and so on. Okay. But so you should, I mean it is all these are, there are several useful tools involving these, okay, and we have just touched upon a few of them here. Okay. Okay. So now I will do a few practice problems. Okay. And the first one is to solve a system of linear equations. Okay. So let us take the system, let us say x plus y plus z equal to 2, and then we have x plus y or 2x minus y equal to 1, and you have x plus 2y minus z equal to 3. Okay. So, suppose you want to solve this system of equations. Okay. So, you want to solve them and get the values of x, y, z. So what you do is you look at your matrix. Okay. So, your the matrix of the matrix of coefficients is 1 1 1, the second row is 2 minus 1 0. So I can write this as 0 times z, okay, and then the third row is 1 2 minus 1. So, this is your matrix of coefficients. Okay. So, this times x y z, this is equal to 2 1 3. So, I can write this in this form. Okay. And so now I can write x as this determinant of 2 1 3 1 minus 1 2 1 0 minus 1 divided by 1 1 1 2 minus 1 0 1 2 minus 1. You can easily calculate, see the denominator, okay, is so this will give you 8 by 8 equal to 1. Okay. Similarly, y is equal to 1 and z equal to 0. This is what you will find. Okay. So you can verify that you get this as a solution, and you can see that if x is 1, y is 1, z is 0, then x plus y is 2, 2x minus y is 1, x plus 2y minus z is 3. Okay. So, solution using Cramer's rule. Okay. Now, the next problem that I want to do, okay, before I go that, let me just mention that you can either solve this using Cramer's rule. So, there is an alternate method using or equivalent method using a technique called Gaussian elimination. Okay, and in this what you do is you do various operations, various elementary row operations, and convert your coefficient matrix to a diagonal matrix. And once you convert it to a diagonal matrix, you can immediately determine the values of x, y, z. Okay. So I will not be doing Gauss elimination, okay, but I expect that you are familiar with Gauss elimination. Okay. Now, the next problem that I want to do is this. So, show that the product of r z theta followed by r x phi, show that the okay, let me not call it a product, show that the operation of r z theta followed by r x phi can be represented by an orthogonal matrix. Okay, and what I mean is you show it explicitly. Okay, so let's try to show this explicitly. So what you mean is you have a vector x y z. You operated on it by r z of theta. So, when you operate on it by r z of theta, so r z of theta is cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1, and then you operate on this vector. Okay, so this operation gives you another vector. Okay, and you operate on this vector by r x of phi. So, what is r x of phi? That is 1 0 0 cos phi minus sin phi cos phi. Okay. So, when you do this, okay, so you get so let me call this x prime, y prime, z prime. Okay. Now, I can write this. What I can do is I can write this. I can do the two matrix multiplication first and then multiply by the vector. Okay. So, suppose I multiply these two matrices, what will I get? So, 1 into cos theta. So, I will get a matrix minus sin theta 0. Okay. Then this second column will be cos phi sin theta minus no, it will just be cos phi sin theta. Okay. This into this, this into this, this into this. Okay. Now, the third, so then now the next element will be 0 into sin phi is 0. So, you have cos phi cos theta and the last one will give me 0 0 and I have minus sin phi. Okay. Now, and the last column we will have 0 sin phi sin theta and 0 sin phi cos theta, then I have 0 0 and I have cos phi. Okay. So, this is what my this product of these two matrices looks like, and this when it operates on x y z will give me x prime y prime z prime. Okay. Now, I will not do this explicitly, but you can show that you can show two things. You can show that this is an orthogonal matrix. You can show that this matrix, okay, is basically orthogonal by showing I mean it is obviously orthogonal because rotation preserves direction preserves magnitude, not direction, preserves magnitude of a vector. Okay. But you can explicitly show this by showing by doing the following. So, x prime is equal to so you say x cos theta minus y sin theta, then you have y prime is equal to x cos phi sin theta plus y cos phi cos theta minus z sin phi, and z prime is equal to x sin phi sin theta plus y sin phi cos theta plus z cos phi. Okay. So, now you can show this explicitly by showing that x prime square plus y prime square plus z prime square is the same as x square plus y square plus z square. Okay. Can show this. This we can prove that r x of phi r z of theta is orthogonal. Okay. So, we sort of went a bit roundabout. Okay. So, we took, I mean, we intuitively know that a product of rotations should be an orthogonal matrix, because a product of rotations, okay, will preserve the magnitude of the vector. Okay. So, if each rotation will preserve the magnitude, so the product should be an orthogonal matrix, but we can show it explicitly by doing by going through this procedure, by seeing what the new coordinates are. Okay. So, this is the final coordinates x prime, y prime and z prime, and we express them in terms of x, y, z. Now, if you square this, you will get various terms. Okay. So, you will get x square cos square theta, you will have y square sin square theta, you will have and you will have the cross terms x y 2 x y cos theta sin theta. Similarly, when you take y prime square, you will get various terms. Okay. And similarly, z prime square will give you various terms, and if you add all of them, you collect all the terms, you will get that they satisfy this relation, and by showing this you can prove that this product of rotations yields an orthogonal matrix. Okay. Yields a matrix that is orthogonal. Another way to do this, yet another way to show this is to look at, so if you say y is equal to r x of phi r z of theta y vector times x. Okay. So, if you take a vector x, okay, you operate it by r z of theta and by r x of phi. Okay. So, I can say I just call the corresponding vector y. Okay. And what you need to show is that y transpose y. Okay. So, if you think of y as a column matrix, then y transpose y is equal to, so now this is transpose of this whole thing. Now, when you take the transpose of this whole thing, you have to take the transpose in the opposite order. So, it is x transpose r z theta transpose r x phi transpose times r x of phi r z of theta x. Okay. So, this is y, this is y, this is y transpose. Okay. Now, I can do this products in this way. So, I multiply these two things first. So, r x of phi transpose r x of phi. Okay. Now, since r x is a rotation about x axis, this is an orthogonal matrix. So, the transpose is nothing but the inverse. So, this product is just the identity. So, I can write this as x transpose r z of theta transpose. This is just identity. So, I do not need to write anything, and so I just copy the r z of theta x. I won't show the vector, okay, in this. So, let me just put vectors onto all the x's. Okay, x's and y's. Okay, so now again I have r z of theta transpose r z of theta, which is nothing but the identity. So this is nothing but the identity matrix. So this equal to x transpose x. Okay, so clearly this product is orthogonal. Okay, so a third way to show it is this, and so if you take product of any two rotations, you get another orthogonal matrix. Next problem that I want to do, okay, has to do with Hermitian matrices. Okay, and so this is problem 3 is this matrix 4 I 2 plus 3 I. Okay, and since I want to talk about Hermitian matrices, I am making it a complex matrix 1 2 minus 3 I 1 3. Is this Hermitian? Okay, and what so if you call this as A equal to this, then A star is equal to 4 minus I. So, you take the complex conjugate of I is minus I, complex conjugate of 2 plus 3 I is 2 minus 3 I, complex conjugate of minus I is I, this is 2 minus I 1 2 plus 3 I 1 3. So, complex conjugate of a real number is just itself. Okay. And if you take A dagger, this is nothing but you take the complex conjugate and then you take the transpose. Okay. So, this is equal to, so you are just going to take the transpose of this matrix, okay, and the transpose of that matrix is just given by 4 I 2 plus 3 I minus I 2 minus I 1 and 2 minus 3 I 1 3. Okay, so this is clearly this is not equal to A. Okay, and the reason it is not equal to A is because of this. Everything else is the same, it is only this 2 minus I, and in this case you had 2 plus I. So, that was the difference. Okay. Now, what I want to emphasize is that for a Hermitian matrix, implies that the diagonal elements have to be real. Okay, so, the diagonal elements of a Hermitian matrix have to be real. The off diagonal elements should be complex conjugates of each other. So, for example, you had a 2 minus I here, a 2 minus 3 I, then you should have a 2 plus 3 I there. Okay. So, that is a condition for a Hermitian matrix. Okay. Now, next part of this problem. Okay. So, problem 3b. Show that eigenvalues of a Hermitian matrix are real. Okay. So, suppose you have a Hermitian matrix, okay, you show that its eigenvalues have to be real. Okay. So, suppose you have a matrix A and x equal to lambda x. So, if A dagger equal to A, then lambda star equal to lambda. Okay, so, you have to show this. This is what you have to show. You have to show that if A is a Hermitian matrix, then its eigenvalues are real. Okay. And you can show this quite easily. So, suppose you take A x equal to lambda x. Okay. Now, this implies that A star, you just take complex conjugates on both sides. So, you get A star x star is equal to lambda star x star. Okay. Now, if you pre multiply by A by x dagger, okay, so you do x dagger A star x star is equal to lambda star x dagger x star. So, now if you do another thing. So, let us say you take the first equation and you take its Hermitian conjugate. So, if you take this equation and take its Hermitian conjugate, you will get, so you will be taking both the transpose and the complex conjugate. So, what you will get is x dagger A dagger. Okay. So, the order changes, because when you take the transpose of a product, you get the product of transpose in the opposite order. Okay. Now, lambda is just a scalar. So, I can just write lambda star and x dagger, I should write x dagger. Okay. So, now if I post multiply by post multiply by x star, yeah. So, now if I post multiply by x, if I just post multiply by x, what I will get is x dagger A dagger x is equal to lambda star x dagger x. Okay. And A dagger x is nothing but A x. Okay. So, this is A x. So, this is equal to A x, this is equal to lambda x. Okay. So, what I get is that lambda times x dagger x is equal to lambda star times x dagger x, or lambda equal to lambda star. Okay. So, implies lambda is real. Okay. So, a Hermitian matrix has real eigenvalues. Further, so distinct, so eigenvectors corresponding to distinct eigenvalues are orthogonal. Okay. And what we mean by this is that suppose you had A x 1 is equal to lambda x 1 and A x 2 equal to mu x 2. Okay. If A is Hermitian, then x 1 dagger x 2 is equal to x 2 dagger x 1 equal to 0. Okay. So, x 1 dagger x 2 is a scalar, and you will be able to show that if this, of course, we are assuming that lambda not equal to mu. So, they are distinct eigenvalues. So, the eigenvectors corresponding to distinct eigenvalues are real. Okay. This is eigenvectors corresponding to distinct eigenvalues are orthogonal. Okay. Now notice that the definition of orthogonality for complex vectors. Okay. So, this involves transpose and conjugate. Okay. So whenever you are dealing with complex vectors or complex matrices, then instead of just doing the transpose, you should do a transpose followed by the complex conjugate. Okay. So this illustrates two properties of Hermitian matrices which are actually extremely important. Okay. So Hermitian matrices are central to quantum mechanics. Okay. So, the Hermitian, so a Hermitian matrix, okay, you can write it, you can write a differential expression for an operator, okay, and so you can define something called a Hermitian operator, or you can write a matrix representation of an operator, and that involves Hermitian matrices. So, the idea of Hermitian quantities, okay, are central to quantum mechanics because they have real eigenvalues. Okay. Eigenvalues corresponds to observed values. Okay. So if you have an observable, then its value should be real. Okay. So, it should have real eigenvalues, and the matrix that has real eigenvalues are the Hermitian is a Hermitian matrix. Okay. So this idea of Hermitian matrices plays a very important role in quantum mechanics. So, with that I will conclude module 2.